Here's a pear tree. We're going to let a pear fall from up here down to about here. As the pear falls, it loses potential energy. And you might say that it loses potential energy because the height decreases. That's true, but there's another reason why it loses potential energy. It loses potential energy because gravity is doing work. After all, gravity exerts a force over some distance. Let's summarize. If you want to add potential energy to the peach, then you have to take your hand and do work against gravity. You have to push up and exert a force some distance so that now you and your force are doing work against gravity. Let's summarize. The exact same thing is true for electric fields. Here's a uniform electric field. We have a positively charged plate on top and a negatively charged plate on bottom, and inside the plates, the field is uniform. That means it's the same strength everywhere, and it points in the same direction everywhere. And we can see that because the arrows are evenly spaced and they all point down. So let's take a charge and put it up here. Does this charge have a lot or a little potential energy? Your intuition might lead you to the correct answer. It has a lot of potential energy. Why? Because it's crammed up near these other positives and it's attracted down to the negatives. So if we let go, the charge will fall down toward the negatives. But wait, why did it fall? It fell because the electric force pulled it down. So that electric field exerted a force over some distance. The electric field did work. And whenever the electric field does positive work, the charge loses potential energy. Let's summarize. If you want to take the same scenario and add potential energy to the charge, you would have to pick it up with your hand and move it up. You are now exerting an upward force over this distance, and so you are the one pushing it up and doing the work. As a result of the work you do against the field, you add potential energy. Let's summarize. We can write down a couple of simple and easy rules to remember. In the top case, this positive charge is moving with the field lines, and as a direct result, it loses potential energy because it's falling to where it wants to naturally go. In the bottom case, this positive charge is moving against the field lines, and as a direct result, it gains potential energy. Because to move it toward these positives, you have to do work and add energy to the system. This idea of work on a charge is going to be really important for us. But wait a second. We don't really talk about force when we talk about charges. We talk about the force per coulomb. And in the exact same way, we are going to be talking about the work per coulomb on a charge. This is called potential difference. Potential difference is the work divided by the amount of charge as the charge moves from one point to the next. More formally, it's the work done per unit charge as a small positive test charge moves from one location to another. The unit for potential difference is simply the unit of work, which is the joule, divided by the unit of charge, the coulomb. And we define a joule per coulomb to be a volt. So this is an easy one to remember because potential difference is represented with a V and its unit is also a V.